So today we will be presenting our momentum video project. So an overview of our project. In this presentation, we will teach you the basic concepts of momentum. We will prove and explain the impulse momentum theorem and the law of conservation of momentum. We will explain the experiments that we went through, and we'll back up our claims with our own data that we found in the experiments. So defining some of the topics that are relevant to momentum. Momentum is the vector quantity of mass of an object times its velocity, and momentum is represented by the vector p. Impulse is represented by the vector j, and is the applied force to an object that causes an equal vector change in its momentum. Both vectors have direction and magnitude and are found using the equations on the next page and described throughout the video. So these are the four equations that are relevant to momentum. So we have momentum, which is the vector p, which is momentum, is equal to mass times the vector velocity. And then impulse is impulse, which is the vector j, is equal to f net times the change in time. And then the impulse momentum theorem is impulse is equal to the change in momentum. And then the law of conservation of momentum is that the momentum is equal, the final momentum is equal to the initial momentum, because momentum should not change within a system throughout an experiment. And then these are three diagrams that we have. The first one just explains momentum in itself. So it's the mass times the velocity of just the ball that we have in this diagram. For each one, it's different velocity, different mass. And then for the impulse, it's the collision of these two. So there's one has a velocity and the other one, and you can see that they have a reaction, which we have represented by the orange, and that after that the force on mass 1 pushes the way that the velocity vector was pointing in the beginning. And then for our third diagram, it is the joining of the two. So in the beginning, you have the momentum of them going towards each other. Then in the second one, they collide, they have impulse on each other. And in the third one, we have that they react with equal velocity in opposite directions.
And then here are the four types of collisions that we will be explaining throughout our presentation. There are elastic collisions, which are bouncy collisions where there's no loss of kinetic energy. There are completely inelastic collisions, which are rigid collisions where the maximum amount of kinetic energy is lost. There are inelastic collisions where these are the most common types and it happens when only some of the kinetic energy is lost in the system. And then explosions where both objects involved are at the same speed before the collision and then gain a sudden burst of momentum.
So now we move to our first lab, which was trying to prove the law of conservation of momentum. The law, once again to reiterate, states that in a collision, within the system, there is no loss or gain of momentum during a collision. And here's the equation in a more expanded frame. We have the mass of object 1 times the velocity of object 1 plus the mass of object 2 times the velocity of object 2. That gives us the combined momentum in the system before the collision, and we see that's equal after the collision. Here's our qualitative example of the law of conservation of momentum. Yeah, so here we see that the Newton's cradle is used to pull back one of the balls, and then the momentum from that ball is reciprocated all the way through the system onto the final ball. Now for our data, we used 4 different types of collisions, all 4 that we listed earlier. And then in each of them, we found what we controlled was the initial momentum of the entire system. And then we used force sensors connect to a lab quest to figure out what the final velocities of the 2 carts were as we collided them together. And using the mass of that, we were able to find the combined momentum before and the combined momentum after. And then linearizing them, we found that our data had a slope of 9.9649, and with just a percent error of 5%, we would say we were pretty successful in proving the law of conservation of momentum. And then here's the videos for our four different types of cart collision. So we have the explosive collision, the elastic collision, the completely inelastic collision, and the inelastic collisions.
And now we're going to move on to our lab about the impulse momentum theorem, which, once again, reiterating, is the law that states that the impulse applied to an object will be equivalent to the change in momentum of that object. And then this vector J equals the change in P, or momentum, is the equation for that. And then this is our qualitative example. So this is going to explain the theorem. So with Andrew compressing his legs during the fall, he extends the time of the collision, which it decreases the amount of force that is applied, which is proving the theorem. And then here's all of our data for our lab. We did 10 different trials, and we tried to use multiple different velocities to get like a wide range of options. Then we calculated using a force sensor the impulse once collided with, and then we found the change in momentum, and then compared that to the impulse that we found. And we should have gotten, with linearization, around a slope of 1, and we got a slope of 1.0656. So with around a 6.5% error, we feel like we also were pretty successful in explaining this theory as well.
And thank you for listening to our presentation.